Okay, let's dive right into this. Welcome back to another explainer. Today, we're unpacking some truly groundbreaking research that could completely revolutionize how we build our homes, our communities, and our cities. We're looking at the fascinating world of sustainable earthen construction, but with a major, high-tech, yet completely natural twist. We're going to explore how we can use biologically synthesized polymers to stabilize earthen materials, effectively turning simple soil into a highly durable, breathing, and completely recyclable building block. If you've ever wondered how we can construct the buildings of tomorrow without destroying the planet today, you are absolutely going to want to pay close attention to this.
Here's our roadmap for today's explainer. We'll cover the earthen construction dilemma, look at natural alternatives, test their strength and durability, explore breathing walls, evaluate the recycling potential, and finally, discuss the future of sustainable building. Let's get into it.
Section 1. The Earthen Construction Dilemma. The Paradox of Eco-Friendly Building.
Before we can really appreciate the solution, we have to deeply understand the paradox of eco-friendly building today. Earthen materials, like rammed earth, have incredible potential, but they have one massive, glaring vulnerability. That vulnerability is water. Unamended earth is incredibly eco-friendly, but it degrades really easily when exposed to the elements. To fix this, the construction industry typically relies on adding roughly 6 to 10% cement to the soil mix. Now, cement definitely does the job. It makes the earth strong and highly durable. But here's the catch. Cement acts as the environmental villain in this story. Adding it gives the material a carbon footprint equivalent to fired bricks or weak concrete. It lowers the material's natural ability to buffer moisture, and worse, the energy-intensive process required to recycle cement-stabilized earth makes it completely uneconomical. So at the end of its life, it basically just gets dumped in a landfill. We need the strength of cement without that heavy environmental penalty.
Section 2. Biopolymers, the natural alternative. Growing our building stabilizers. What if instead of mining and burning limestone to make cement, we actually grew our building stabilizers? This research explores two widely available industrial biopolymers. First, we have guar gum, which is extracted from the endosperm of cluster beans. And second, xanthan gum, which is synthesized from a plant-based bacterium. To understand exactly how these plant-based powders hold a building together, we have to look at the microscopic level. When these biopolymers interact with water, they form what's called a hydrogel. Think of this as a microscopic organic glue. Over the first hour or so, this hydrogel sits in a rubbery state. But as the soil dries out over the course of 3 to 5 weeks, it slowly transitions into a hardened, glassy state. During this process, the hydrogels actively bind the soil particles together. Guar gum does this using hydrogen bonds, while xanthan gum packs an extra punch by adding stronger ionic bonds into the mix.
So the absolutely crucial point to remember here is this specific number, 1.5 to 2.0%. The researchers found that adding just 1.5 to 2.0% of these biopolymers by dry mass achieves the exact same air-dried compressive strength as earthen materials stabilized with 8.0% cement. That is a massive wow factor. We are literally talking about replacing a highly pollutive industrial material with a tiny fraction of a biologically synthesized alternative and getting the exact same structural integrity.
Section 3. Testing strength and durability. Putting bricks through the gauntlet.
Now, compressive strength is great, but as we discussed, the real enemy of earthen construction is water. So the researchers designed a series of brutal, highly controlled laboratory obstacle courses to simulate real-world weathering. First up is the Geelong Drip test. This is specifically designed to simulate the erosive power of heavy rainfall over time. In this test, water is actively pumped and dripped directly onto cylindrical and tiled earthen samples from exactly 400 millimeters above. This relentless dripping goes on for a full 60 minutes, and then the researchers measure exactly how deep the water has eroded into the material.
The contrast in the data here is just wild. The unamended earth eroded significantly, losing 8 to 10 millimeters of material, but the biopolymers? Both of them stayed well under the critical 5 millimeter threshold. The guar gum eroded about 2.5 millimeters, and the xanthan gum performed even better, keeping erosion under 2 millimeters. This formally classifies the biopolymer materials as slightly erodible, proving they can genuinely stand up to aggressive, direct rainfall without washing away. The xanthan gum edges out a slight victory here simply because those extra ionic bonds we emphasized earlier give it a slightly higher tensile strength as the hydrogel cures.
And this next test brilliantly illustrates what happens in worse conditions. This is the dip test. It doesn't just simulate rain, it simulates sudden, severe flooding by completely immersing the bottom of the bricks in water for 10 straight minutes. while they're suspended in midair. The unamended earth essentially just visually deteriorates, falling apart right into the water bath. But the guar and xanthan gum samples, they remain remarkably intact. They maintain their sharp edges and structural shape despite the sudden total immersion.
When we summarize these gauntlet results using official DIN standards, the impact is undeniable. The unamended earth falls into Class 3, meaning it is strictly suitable for interior walls only. It just can't handle the outdoors. But adding those tiny fractions of biopolymers bumps the material all the way up to Class A. This formally proves they are completely suitable for external walls exposed to natural weathering. You literally do not need cement to stop your house from melting in the rain.
Section 4. Breathing walls, moisture buffering, how biopolymers regulate humidity. Let's pivot away from pure strength and durability for a moment and look at a crucial green metric: how these materials actually make a building feel to live in. This brings us to a concept called moisture buffering value, or MBV. Simply put, this is the ability of a wall to act like a sponge for humidity, absorbing excess moisture from the air when it's damp and naturally releasing it back when the air is dry. Materials with a high MBV create what we call breathing walls. This keeps indoor environments incredibly comfortable and healthy naturally, which can dramatically lower your reliance on energy-heavy HVAC systems. So let's compare our materials against that villain we talked about: cement. Unamended soil has a baseline MBV of about 0.7. When you add cement to make the wall strong, the cement actually coats the clay particles and clogs the pores, dropping the MBV down to a dismal 0.55. But because biopolymer hydrogels have a natural inherent affinity for water, they don't just maintain the wall's breathability, they actually boost it. The biopolymer materials push the MBV up to between 1.0 and 1.15, shifting their classification from moderate up to good. So you get the strength of cement, but you also get a building that actively manages its own indoor air quality. That's a real win-win. Section 5. Recyclability and soil washing, the end-of-life potential.
Let's move to the end of the building's life cycle and see how this builds a truly circular economy rather than a one-way ticket to the landfill. When a cement building comes down, recycling it is an absolute nightmare. But with biopolymers, we can use a process called soil washing. However, the data reveals a fascinating trade-off between our two hero materials. Remember those extra ionic bonds that made xanthan gum slightly better at resisting rainfall? Well, those stronger bonds mean that during soil washing, xanthan leaves behind some stubborn agglomerations that resist breaking down. Guar gum, on the other hand, relies on slightly weaker hydrogen bonds. During washing, those bonds easily dissolve, returning the material almost perfectly to its original soil properties, with just a slight tweak to the fine fractions needed for reuse. So xanthan is your champion for maximum weather resistance, but guar is your absolute champion for seamless recyclability. Section 6. The future of sustainable building, the final verdict. We've looked at the chemistry, the rigorous erosion tests, the hygroscopic data, and the end-of-life recycling. Let's bring the final verdict together. The core takeaway from this extensive research is that we no longer have to compromise. We can eliminate the need for high-carbon, pollutive cement in earthen construction. By utilizing just 1.5 to 2.0% of natural biopolymers, we achieve excellent structural strength. These materials prove they can survive extreme weather, from heavy rainfall erosion in the Geelong Drip test to sudden floods in the Dip test. Unlike cement, they actually improve the indoor environment by creating breathing walls with high moisture buffering. And depending on your specific project needs, you can choose xanthan for peak strength or guar for ultimate easy recyclability. All of this empirical data points to a massive paradigm shift in how we approach green architecture. We're looking at a future where our structural stabilizers aren't mined and fired in massive industrial kilns, but are instead synthesized and grown biologically. It fundamentally challenges our reliance on traditional, carbon-heavy methods. So I'll leave you with this final, provocative thought. With all of this data proving that biology can match and, in some ways, exceed the performance of industrial cement, is it finally time to start growing our buildings? Think about that. Thank you so much for joining me on this explainer, and I really hope this sparks your curiosity to keep exploring the incredible innovations happening right now in sustainable design.